Good morning, everyone. Welcome back. We're going to start today's class with a few miscellaneous clarifications, and then I'm going to talk about this week's quiz a little bit. So to start, this example of a circular linked list flustered me a bit last class, and I just wanted to go over it after I had an opportunity to look at it for 5 more seconds. I got confused about removing the front entry because if this is the back, then I was worried that this was the front for some reason, and then to get to here, we would have to linearly go through every node. That would be dumb. And I think this is a good example of how circular linked lists can be a bit confusing. If you don't have this pointer to the back of the list, then any of these nodes could be the back. And it follows that every one of those nodes can be the front. But if this is the back, then the node after that is the front because it loops back on itself. So we already found that a new entry can be added at the back or the front, depending how you look at it, in constant time. And the front entry can indeed also be removed in constant time. You would just go back dot link equals back dot link dot link. And then the garbage collector will eventually notice that nothing points to the former front entry and delete it. So then the fact that I wanted to go over this again reminded me that fact 4.2 looked initially strange in the lecture as well. I wanted to go back to this because late in assignment 2, I don't want to say you're supposed to use it because every one of those questions has many different ways you can get to the conclusion. But my solution to one of the later problems uses fact 4.2. In the lecture, I saw it for the first time in a while and wasn't sure if it was a constant or what. It's a function. We don't have any conditions on G, similar to what we had for fact 4.1, because fact 4.2 can be used for any function of G. Remember that big omega is sort of like greater than, so it makes sense that if f is greater than h, then f plus anything positive is also going to be greater than h. So yeah, that's any function. Last miscellaneous thing is sort of a overview of both this lecture and the next quiz. We're going to talk today about an application of stacks, which is arithmetic expression parsing. And then the rest of the week will be spent talking more about the table ADT and an accompanying data structure called a hash table that is really good for implementing that ADT. So on this week's quiz, the first question is definitely going to be, I have no idea where it is, but one of those questions, one of these tables where you have a bunch of operations on a stack and or a queue, and you have to write down the return value and the state of the stack. And then the reason I talked about the topics covered today before talking about the quiz is that I haven't finished making the quiz. There's going to be a question about tables and hash tables. If we get far enough today to justify me asking a meaningful question about that, if we only get far enough for a general overview, it's going to be about this sort of stuff. So if there are no questions needed for clarification, we'll get right on with the content. At the end of last class, we found that there's another way to write arithmetic expressions, in fact, two ways, that make the order of operations unambiguous. If you have an expression in this postfix notation or the related prefix notation, then it's unnecessary to use brackets to specify which operation to do first. This also makes it so there's a nice little algorithm for evaluating these expressions that is a nice application of stacks. Before we look at the algorithm, though, we'll just go a bit deeper into postfix notation. I'm going to do these exercises, and feel free to follow along. Eight times 4 plus 7. This is also a good example of the whole unambiguous order of operations thing. If it weren't for the brackets, we would just cite the order of operations, the rules, which are actually arbitrary. There's no true mathematical reason for doing it that way. We would have to cite the order of operations, and if you posted this on Facebook or whatever, you'd get a bunch of boomers arguing over which order of operations is the correct one. But for this, we can write four, 7 plus to denote 4 plus 7, and then 8 around that, and the star after that to denote that you have to multiply 8 by the result of 4 plus 7. I think this notation will also make more sense once you see the algorithm for evaluating it, so stay tuned for that. The next expression is a bit more complicated, but a sort of, I guess you could call this an algorithm, a human algorithm, for doing this is to rewrite the infix expressions as postfix in the same order that you'd evaluate the operations in infix notation. So this 6 divided by 2 is in the most nested fraction of this expression. So I would evaluate this first when solving it. Likewise, I would first write 6, 2, slash. And then we see some more brackets here, so we don't have to consider the 3 yet. We're adding that to 5. So we add a 5 and the plus to denote the result of 6 divided by 2 and 5. We add them. Also note that for commutative expression or commutative operations like addition, so order doesn't matter, you can write the numbers in a different order and still get a correct result. For instance, writing it like this would still denote the same thing. Take the result of dividing 6 and 2 and 5 and add them. However, I'm writing these numbers in a specific order this way in order to preserve the original ordering of the numbers, just for aesthetics. Finally, we're going to multiply 3 by the result of all this. So we put a 3 there and a star there. I'm wondering, should I evaluate these or move on to the big example? I'm going to convert this and then evaluate one or all of them when we're looking at the algorithm. So this one's intense. I would probably evaluate this 6/2 first in infix because it's so deeply nested. And then +5. Three times that whole thing. And then I think, yeah, we would want to do this 3 times that next. Wait. Oh wait, I did do the 3 times that. Trying to figure out if I can write this without inserting any symbols between 2 symbols that I had written before, but I don't think I'm going to be able to do that. Yeah, our next operation would be the result of 4 + 7 minus this 3. No, that 8 times 4 + 7 minus 3. This is going to be messy. On the quiz, the difficulty level would be more like A or B, not like C. I'm just going to start writing numbers spaced out and put the operations where they need to be. So 4 + 7 are added, so I'm going to put a plus after 4 and 7. Eight is multiplied by that, so I'll put a star such that the 8 and the star for multiply have 4, 7, and the addition symbol between them. And then I think that resolves everything in our brackets. No, we still have to subtract this whole thing from that whole thing. So we put the operator after the operands as usual. And finally, we have 9 plus all that plus. So I put these numbers super spaced out because I wasn't sure exactly where I would have to put the operands. And you see that I generally didn't have to put many operands between the operators except for shoving both the plus and the times between the 7 and the 3. So I'm just going to rewrite 9, 8, and 4. Okay, everything looks good. It looks correct. Please call me out if there's some discrepancy between what I wrote and what's on the slides. But we're going to revisit these soon once we know about the algorithm for solving these. As I've been saying, you can use a stack. So you might get an input that looks like this. This represents an expression in postfix notation. And what the algorithm is going to do is take or look through the string character by character, and then if the current character is, what the heck? If it's a number, put it on the stack. And if it's an operator, pop the most recent 2 items from the stack, evaluate that operation, and then push the result back onto the stack. So say we have an expression 847 plus times. We have a stack and we go through the expression character by character. This is a number, so we put it onto the stack. Now we're looking at 4. Push that to the stack. 7. That's also a number. Put that on the stack. And then we have a plus. So for an operator, we take the inputs by popping the most recent numbers from the stack, and then evaluating the operation on them. In this case, addition. And then we put the answer to that back into the stack. Moving on, we see multiplication. We pop the most recent 2 numbers off the stack. Evaluate this. And put the result into the stack. Sweet. There we go. Put like this. It should be more helpful when you download these slides from the website. Now that we're done looking through the string, oh yeah, pretend I underlined the asterisks when we got to the multiplication. Now that we're at the end of the string, we return the top value of the stack, assuming the input is like correctly formatted. You could probably validate that by making sure that there's at least one or exactly one element on the stack by calling isEmpty after popping. But assuming the expression is formatted correctly, the thing that you pop will be the result of that arithmetic expression. I think I'm going to do example B from earlier in the slides because that has some operations or operators that are in between values. It's not just number, 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 operation, operation. You'll be able to see the stack in action more with example B. I'm not going to touch example C. It scares me, but maybe you should. I hate adding new pages. All right, let's solve this. 3, 6, 2, those are all numbers. We're going to push those onto the stack. The slash symbol is an operator, division. So we pop 6 and 2 off the stack. Evaluate it, and push the result back onto the stack. Moving on, 5 is a number. Plus is an operator. Actually, I'm going to try writing all states of the stack, kind of like that upcoming quiz question, just to make this more useful as an example of the algorithm's execution after the fact. Okay, we pushed all those onto the stack. And then we popped 6 and 2 and divided them. And pushed the result back onto the stack. Then we pushed 5. We're going to add the most recent 2 operands. Push the result, and then for multiplication, again, pop the last 2 operands, evaluate the operation, and push the result back onto the stack. That's 24, right? Yippee! I can try and draw the digits real close together so you know that it's a 2-digit number. That's the end of that execution. The last line of the algorithm would return the popped value on the stack, which in this case is 24. So the entire expression evaluates to 24. Hopefully that made some sense. And also, to justify this a bit more, you could try implementing an algorithm for parsing arithmetic expressions that doesn't use a stack and see how clunky that gets. Using an array that just happens to work just like a stack would be cheating. I also wanted to mention that we've been talking all about postfix, but very similar rules apply for prefix notation. It's a bit messier though. It kind of violates the contract of a stack to do this, or to evaluate a prefix notation expression from left to right. You would have to push values onto the stack until you've seen two numbers, and then pop another element off the stack, and it should be an operator if the if the expression is formatted correctly. So you could evaluate this, or you could implement this by like repeatedly pushing it, checking, and popping, checking, and then pushing back in. Or you could make a special stack that lets you look into the stack beyond the top value. Neither solution sounds very fun to me. So much easier to evaluate a prefix notation expression is to simply use our algorithm that we just saw for postfix, but go through the string backwards. You could see that this would push 2, then 3, then multiply them, then push 6, and then add 6 plus the result of 3 and 2, which is the same as our infix expression. It would just work. We covered postfix and postfix only because it has the nicest algorithm, but prefix has a almost as nice algorithm. You just go through it in reverse. All right, that's it for stacks and queues. Let's see if we're able to talk about tables enough to include them on the quiz. We've talked a bit about tables before, but we're going to go deeper into them, including finding an implementation that uses a new data structure beyond arrays and linked lists to make searching really efficient. So recall that each entry in a table contains a key, a unique identifier for the entry, and the number itself. So you might make something like a phone book that maps phone numbers to names, or you might have something for looking up students' grades, student number to grades. Wonder if I could think of an example that doesn't use numbers. I don't know, you could map name to some quality, like favorite color, I don't know. The phone book example is much more useful. And of course, we've been talking about applications in a school environment in previous examples, so like looking up grades by student number. All those examples are cases where you would want to use a dictionary. Each key in a table is unique. No duplicates are allowed. That's why my examples tended towards using numbers, because those would be unique identifiers, as opposed to names which can be shared. Also, the entries are not in any particular order. Student with student number 7865458 doesn't need to be right next to student with student number 7865459 in the data structure. They could be in completely different places in memory. If you take distributed computing, Comp 3010, Rob might make you make a distributed hash table. In that case, two entries that would seemingly be right next to each other might actually be on entirely different computers. I'll go through this kind of quickly because we already did a more informal listing of operations. But with a table, you can insert an entry with a specific key to the table. Depending on the application, the insert method may or may not take a key explicitly. Alternatively, the key might be some property of the entry that can be easily derived. Like for the class management example, maybe I already have a file that contains everyone's names and student numbers. So I can just say insert that row of the table, table as in file, into table as in data structure. And then it would internally take the student number as the key and everything else as the entry. Delete removes the entry with the specified key from the table. And then search and retrieve works similarly to find the entry associated with the key. Search K determines whether there's an entry with key K and just returns whether it exists or not. Is this student in my class? Does this phone number correspond to a real person? And then retrieve returns the data associated with it. The constructor is empty, is full, and print do exactly what you'd expect. These operations tend to appear a lot in different ADTs. When you're programming in general, like this is just an aside on some real world stuff, a really good approach is to start by thinking about the ADT without regard to the data structure. Like, if you've been asked to make that student management system and your first thought is, I should use a linked list, probably doing it wrong. Especially if you need a more specialized ADT like a stack or a queue. Think about the operations that you need. What kind of ADT gives you those operations? And then, like, to be honest, after this course, you won't be implementing any ADTs probably. You'll be using the ones built into your language or framework. We make you implement ADTs yourself to give you a thorough knowledge on how they work, blah, blah, blah. Anyway, you figure out what ADTs you use first. And then, like I said, you won't really be implementing yourself, but it is valuable to be able to choose an implementation of your ADT. Sort of like that table example on the last quiz, there were meaningful design decisions to be made about whether you should use an array or a linked list based on the specifics of your problem. So if you're doing that in the real world, you might find that your language has a built-in table that's linked list based and a table that's array based, and then you would choose between them. You would choose quite wisely because you took this course. Testing them is also not applicable if you're using built-in ADTs, but I don't know, if you're making a specialized ADT, in the real world, you probably would end up implementing it yourself. So if so, you would test them. Once you know what ADT you need to use and have a solid implementation of it, then you go back to solving the original problem. Back to tables. So how do you implement a table? Turns out all possible answers for that quiz question last week were kind of wrong. Neither arrays nor linked lists are that good. No, wait. That was fine because the quiz question had very infrequent searches, so the linear time searches were just fine. That quiz was fine. But let's say you're running a kind of terrible business. You get a lot of returns. People do not like your product. So in that modified version of the quiz scenario, you would have to search through the table a lot. Maybe insert items less often. And also you could imagine in the classroom scenario and the phone book scenario, you would want to search up students or phone numbers a lot more often than you would want to add new ones. So the situation where you have frequent searches is very much a real world situation. And both of the data structures we know about currently take linear time to search. A table with 10 times more items in it will take 10 times longer to search. You can make some choices about whether the data structures are sorted or unsorted. In fact, you can have a sorted array that gives you access to binary search, which is O of log n, faster than O of n, but slower than constant time. And then you could make some trade-offs for operations that we don't currently care about. What I want to emphasize is that sorting is never constant time with the data structures we already know about. There are data structures that can do more operations in logarithmic time. Skip lists are like linked lists with links between items that aren't directly next to each other. I don't think, or this doesn't come up on the slides for this course, but might be involved in an assignment. And then balanced binary trees we'll talk about later, for sure. So those can be done in logarithmic time, quite efficient compared to linear, but we want to attempt to get search to run in O of 1 time. Can we be given a key and find the item associated with it in an amount of time that doesn't depend on the number of items in the table at all? Can we write a search function that doesn't use a loop? Yeah. This newfangled data structure that does this is called a hash table. And its big claim to fame is that it can do search in constant time. It's O of 1, so no matter how many items are in the table, it takes the same amount of time to do its thing, every time. The way that we create a hash table in code is like, it's actually just using an array. It kind of blurs the line between data structure and ADT because we know for sure that arrays are a data structure and we implement a hash table using an array. But we still consider a hash table to be a data structure because even if it uses another data structure internally, it can't be implemented using a linked list, so you don't get that implementation choice. And the way that you use it is different enough from an array that it's worth thinking about as an entirely separate thing. I think the thing about having no implementation choice between array and linked list is a more valuable thing to remember, though, in terms of why a hash table is a data structure and not an ADT. The implementation of a hash table uses the fact that arrays have the ability random access. Random in this case just means not in any particular order. You have an array of size 10, you can access element 5, then element 9, and then element 0, all at the same speed and regardless of order. You don't have that for linked lists, because then you would have to, with a linked list, you'd have to go linearly through the list, getting the 9th item in a linked list would require traversing the first, then the second, and the third, all the way up to 9. The hash table will use the random access property. And you can actually make a incredibly simple hash table by just making it work identically to an array. But we'll soon see that it's more complicated than that. Instead of using the more familiar array indexing, we're going to use what's called a hash function that maps each key to an array index. So it takes in a key, returns an array index, and thus the implementation of insert key and data would calculate the hash of the key and then add the entry D for data at index h of k, the hash function of the key, in the array. The search method calculates a hash function and then checks that index in the array and just sees if it exists there. H of k should only require constant time to calculate. If it depends on other entries in the list, or other entries in the table, and especially if it depends on how many such entries there are, then we failed. May as well just use a regular array. If the hash function takes constant time to calculate, then we'll be able to perform insertions and searches and everything that follows from that, like deletions, in constant time. The simplest possible hash function is just taking the keys and using them directly as array indices. H of k equals k. This is pretty crappy. I think the phone book and student lookup examples are good examples of this. A phone number is 10 digits. So if you want to use those keys as array indexes or indices, then you'll end up ignoring all 9-digit indices, or 9-digit or less indices, which is a humongous waste of space. You'll probably end up wasting at least half of the memory that you use. Additionally, you could have keys that aren't numbers. Maybe you're working on another distributed computing concept, DNS, and you have to map website names to the IP addresses of the servers that host them. A website name isn't a number. there are ways to convert names into numbers, at least one of which we'll go over in class. But like, you can't use that key directly. You need to do some operation on that alphanumeric key in order to turn it into an array index. So let's see an example that sort of motivates us to make a smarter hash function. You have items in a catalog that are identified by some sort of 4-digit code, and you're creating a table that will hold up to 200 items. Oh yeah, by the way, since arrays hold a fixed amount of, or use up a fixed amount of memory, that means that hash tables inherently have size limitations. So in your implementation of a hash table, and indeed any implementation of a hash table that you see in the real world, there will need to be either some sort of size constraint, like a maximum size, or an algorithm to resize the hash table when needed. So you want to map codes from 1000 to 9999 to indices between 0 and 199. Obviously, we can't just use that simple function, that identity function, you could even call it. We can't use that because all of the keys will cause an array index out of bounds error. So here's a attempt at making it a better hash function. You could use the modulo operation. Recall that P modulo Q equals R means that if you divide P by Q, you'll get remainder R. R has the convenient property that it's between 0 and Q, and we can use that in our solution. If we get the remainder of that numerical ID code mod the size of our hash table, in this case 200, then we can get a number between 0 and n-1, 199, and that gives us a valid array index. We call this a compression map because it sort of compresses one range of numbers into another. We'll find that this modulo operation isn't actually that good at being a hash function. And that's because of a concept called collisions. Basically, two numerical ID code, whatever they called it, they could map to the exact same array index, and that presents problems. You can't store two things in one memory slot. In future classes, we'll learn some ways to deal with collisions. But for now, we just know that they shouldn't happen. We don't have any control over the keys, but we can smartly make our hash function such that collisions are minimized. I'm going to stop there. I don't want to make any guarantees about the contents of the quiz question because this will take some thinking after class, but I don't think we covered enough about hash tables for me to really ask you about anything. Expect a question about arithmetic expression parsing, but also expect the unexpected because I might still ask something basic about hash tables. All right, that's all for now. See you all on Friday.